Talks. Today we have Emily Hannigan. Emily completed her undergraduate degree in electrical engineering and computer science at the University of Illinois Urbana-Champaign in 2016. She's currently finishing her PhD in mechanical engineering at Columbia University. Her work focuses on multiple aspects of improving robot motor control. Her first line of research investigating the use of model predictive control to learn locomotion for simulated snake robots that was robust to significant changes in the environment. And her current work dives into improving methods for learning data-driven dynamics models for robotics control. Her thesis develops methods for improving long-term accuracy of data-driven forward models, as well as new methods for learning useful lower dimensional state representations for use in forward models. She would like to continue this work with the explorations for deep sea and space. So that's exciting. Welcome, Emily. We are looking forward to your talk.
Awesome. Thank you for having me. Let me make sure this is on full screen. All right. So, yeah, as Gabriella said, next week is my defense. So, this is kind of a this presentation is geared towards what the defense is going to be. It should be around 45 to 50 minutes long. I tried to do my best to give a pretty good high-level understanding of everything, but if anyone wants me to go back and explain everything, especially because you're not my committee and there may be some specifics that maybe I dive too deep into for this type of talk, please just let me know, raise your hand, and I can go back to things and update things as we go. So today I'm going to be talking about the work that I've done over the past 6 years doing my PhD, and the general theme of everything I've worked on is the creation and use of forward models in robot motor control. So what is robot motor control? I mean, it's basically anything that you want to do with a robot. How do you make a robot do a specific task? That can be from dexterous manipulation using a robot hand to solve a Rubik's Cube. It can be more generalized locomotion movement, like the Atlas doing a backflip. But basically, any kind of robot motor control is you have a robot and you have some kind of goal. And what we want to do is come up with a sequence of actions that help us perform a task or reach this goal. So let's say we have this robot arm, we want to pick an apple. We need to find an action that will move us closer to our final goal, with the hope of finally reaching it in the end. This sounds simple, but it's a very complicated problem, and it is something that is currently open topic of research. So, oops. Okay, so there's three major categories of or modes of attack to achieve robot motor control. The first is the more traditional optimal control, which includes model predicted control, such as like iterative linear quadratic regulators. More recently, there's been a lot of work in model-based reinforcement learning as well as model-free reinforcement learning, and these are often done in simulation, but they're slowly moving into the real world. But one of the arguments and one of the main areas of research that is still lacking is the actual development of the models for these systems. So optimal control requires a model, model-based RL requires a model, and we're also going to argue that in a minute how model-free RL also benefits from a model. And that is the basis of a lot of my research, is that in order to develop advanced methods of robot motor control, we first need to develop models for these controllers to use. So a model is any function, simulator, algorithm that takes the current state of your system, which would be the robot and the surrounding environment, and it takes an action and it predicts what's going to happen to the robot and the environment when that action is taken. This is useful for all three methods. So optimal control is one of the oldest type of control that we have and is very robust. What we do is you have a real robot, you take its current state, and your controller tests a bunch of different trajectories. So we've got a set of green actions, a set of yellow actions, and a set of red actions. It uses its internal model, which may not be perfect, but it uses it to approximate what's going to happen if we take this action or the sequence of actions. The controller chooses the option that gets us closest to our goal. It then takes the action on the real robot, and then we read that new state and then perform it again. So it's a model that it's a controller that runs in real time, and it uses a model as imagination to figure out to do its best to think of actions that it can take without having to actually take them, which saves a lot of time and also can prevent catastrophic errors if it knows that if it knows that the action is going to result in going too fast or hitting an obstacle, it can choose not to take that action. Model-based RL, or reinforcement learning, is essentially building off of optimal control. It performs the same task, and it has a model, but generally this model is learned, and as we take actions and observe our resulting states, we keep track of that data, and we can use that to update our model in real time in order to make it more accurate for its specific environment that we're in, or to even just learn a model from scratch by exploring. Finally, we have model-free RL, which you may ask, if it says model-free, how are we going to argue that it needs a model? Model-free RL is great in that we learn a policy, which is the same as a controller, by taking actions. It starts off randomly, and then you maybe have different heuristics for how to choose actions, but it performs those actions on the real robot in the real world, and it's very sample and efficient. So we may need to take millions of actions on a robot in order to learn a single task, such as picking up an object. If you want to learn a new task, you have to repeat that again, and it's generally not feasible to train a policy in the real world because it's too expensive and takes too much time. So the general practice is that people simulate their robot, and then you learn your controller or your policy in simulation, and then you transfer it to the real world. And a simulator is just another word for a model. So we argue that models are critical for the main three types of control for learning robot skills today. And now we're going to dive into some of the challenges that the field currently faces in how models perform and act. And we'll talk about some of the different contributions that I've made throughout the past 6 years to improve how models are learned and perform. So when we talk about a model, we also we're going to be talking only about a very specific type of model. So models can be anything from a very specific analytical equation, like a differential equation for a pendulum. It can also be a generalized set of equations, which is a simulator. So things like Majoko or Drake, where we use general equations for how rigid bodies interact with each other. But the issue with this is that often, in order to make it very generalizable to represent anything that we want, a lot of approximations have to be made in the physics computation, and so the simulator is often not going to be very close to real life. The third method, which is the most recent method being explored is data-driven models, where you learn a function. Generally it's a neural network, but there's also other methods. There's Gaussian processes. We're going to be focusing on using neural networks to learn forward models today. This is a very exciting new area of research, and there's still a lot of places for improvement. So actually, let me start with the challenges. So some of the challenges in learning a forward model is that we have to deal with things such as compounding error, which is dealing with accuracy when you're predicting over a long horizon. We also have to handle high dimensional systems, which often results in a lot of problems. And then there's also different effects of the training data distribution and methods of evaluating the forward models that we're going to dive into today. So before we get into things, let me just go over a lot of the nomenclature and diagrams that I'm going to be using to hopefully make it easier for everyone to understand. So when I talk about a forward model, when it's a neural network, that's anything that is a trapezoid is going to be some kind of learned neural network. A forward model is going to be this imagined or a simulated model. Anything that's not the real robot is going to be in a cloud to simulate that it's imagined or learned. The state is usually going to be in blue. That's the state of the system. We have an action that we take, and then this model predicts the next state given the current state and action. And the prediction is usually in light blue, and then we usually need to compare it to the actual next state that we would find from using the actual robot and not the model of it. In equation format, X is our state, A is our action. Our model is sometimes referred to as a function F that we're learning, and that's what the neural network is. And then we're predicting the state at the next time step. And the hat represents predicted, and then the true value will not have a hat. And then just to help put it in a little bit more context for anyone who is familiar with machine learning, the f of x of a is the neural network. The features that we use to train is the concatenation of x and a, and then the label is the true next state. Okay, so let's start with some challenges. So one issue with learning any kind of model is that small inaccuracies will build up over time and cause problems. So if you have an initial state, the top one is our true robot. The bottom one is our learned model. We start off at the same state and we give it an action. We predict the next state with our model, and then we get the true next state with the real robot. And you notice that there's always going to be a little bit of error in what our model predicts, which is fine for a single step. That's not too high. But now if you want to keep using your model to, let's say you have 5 actions that you want to test what happens if you take these 5 actions in order, you have to continually apply your model using an estimated state. And so now every little error is going to slowly accumulate, and the state at the end of that trajectory of actions is going to be much farther apart than just the single step. So we want to find ways to overcome this. When you learn a forward model, generally the function that we're trying to approximate is represented by a neural network, and we learn this model or this function by reducing the error between the true next state and the predicted next state. So the loss is the mean squared error between these two, between the predicted and true state, and then we update our function to try and minimize that. And we're going to call that a single step forward model. So we're only looking one step into the future. We hypothesize that if we use our model to predict multiple steps into the future and use the summation of multiple predictions to compute our loss, which we then use to update our function f, that will improve our model's performance when we use it for multiple actions over a long horizon. The second challenge that we're going to tackle is high dimensional state spaces. So let's say your state that your robot observes is not just, a few joint positions. What if it's an image or a very high dimensional system? When you're predicting, if you're trying to predict a state that has 1,000 dimensions, it is very difficult to accurately reproduce every single dimension. And the mean squared error is tricky because it gives equal weight to every single dimension, even though generally if it's an image or if it's in most high dimensional systems, the true lower dimensional state of the robot is going to be much smaller than if an image shows a ball bouncing, all you really care about is the position of the ball. So maybe if it's 1,000 pixels, you could reduce that down to an X position and Y position of the ball and use that for prediction instead. And we would like to be learning forward models in that lower dimensional space. And we have different ways that we're going to try to do that. So I gave the example of the bouncing ball. Here's an example with the actual environment we're going to be using. Let's say we have a pendulum. You can represent a pendulum using just the joint angle, and then it has a torque that can be applied at a motor at the base. A single differential equation can describe the entire system, and the state representation is just Q0 and then the joint position and the joint velocity within action of a single action. We're going to artificially inflate our state space. We know that a pendulum can be represented by a single joint position, but we're going to represent it with a 2D Cartesian coordinate in order to create a nice toy problem for us to use where we know that our state has 4 dimensions here, but we know that we should be able to get it down to 2 dimensions in the end. So the current practice for reducing the dimensionality of a high dimensional system is to learn an autoencoder. An autoencoder is a set of 2 functions, an encoder and a decoder. They're usually neural networks. And what you do is you know that if your current state has, let's say it's that 4-dimensional system, but we know that it really only needs 2 dimensions in order to truly represent the entire system. So if we can find a function that takes our state and transforms it down into a lower dimension, if we can then create another function that reverses that without any loss of information so that the reconstructed state fully matches the original state, then we know that this reduced space or this latent space, we use that as our new state. And then this is called an autoencoder. The problem with this is that oftentimes it will overfit, and in scenarios that are not as obvious as maybe in our pendulum system, it's obvious that we start with 4 dimensions. We know we can go down to 2. But let's say it is an image and we want to, how many dimensions, if there's 2 balls bouncing, if there's 1 ball versus 2 ball, how do you know that the latent space you find is what is actually going to be useful for learning a forward model? We want to be able to take our state, reduce it, and then be able to use it still as our model, as the state in our model. Using a regular autoencoder can often overfit to parameters, and we're not always learning the best variables for learning a forward model. So our contribution is an idea we call context training. So what if instead of learning a simple autoencoder where you just encode and decode the original state, what if we learn these 2 functions, the encoder function and the decoder function, while we're also learning our forward model function? We hypothesize that this will pressure the encoder and decoder to learn a latent space that is more useful for learning a forward model. We test a bunch of different architectures that I will go into later, but that's one of the main contributions of this thesis. So we are going to, the main two contributions are improving learned model accuracy over a long horizon, as well as using context training to improve the lower dimensional state representation of a state for learning a model. And then we'll also have a few different applications that we'll go over of these improvements, as well as focusing on different methods of evaluation. So first, when we deal with improving long-term accuracy, our hypothesis was that we can change the loss function in order to include more predictions, and we hypothesize that that will result in better accuracy for our predictions over a longer horizon. Our test environment is going to be a 3-link pendulum, and our state is going to be in Cartesian space, and then we have 3 actions, and we're going to be predicting our state at the next time step still in Cartesian space. We're not worrying about latent spaces for this example. We're just worrying about long-term accuracy. So if we learn a model to predict all of the future state variables using the single step versus the multi-step loss function, we can see that multi-step does perform significantly better than the single step when we try and predict over a 50-step horizon. Let's take a second to kind of dive into these results. So the left-hand side is the median error, and the right-hand side is the mean error. We notice that they both help us draw the same conclusion, that multi-step does have a lower overall error than single step. But if you look closely at the y values, you'll notice that the order of magnitude for the median error is about 10 times better than the mean error. And at the same time, this is generally when you look at papers that go over learning forward models, this is about all that happens in terms of evaluation. You'll get a mean loss and maybe a median error, but this is all that you'll end up seeing. But we found that this was generally not enough to really draw a lot of conclusions, and one of our kind of less obvious contributions of this thesis is that the rigor of the evaluation methods that we're going to use. And we propose that these are methods that should be used anytime that a forward model is analyzed. So first of all, what do these numbers mean? We want to know why the mean and the median are so different. So we look at the nth order statistics, or basically a box plot, where we can see the median is this middle line in all the boxes, and the mean is the dotted line above. We can see that most of the data stays around the median, and the reason the mean performs so poorly is that there are huge outliers in our test data set that pull the mean much farther away. We will talk about the consequences of this later, but for now, we just want to highlight how looking at the full distribution of the data can really show that, yes, the performance of the multi-step is, like in the majority of the time, is better than the single step, and that as we predict farther and farther into the horizon, so the first one is predicting a single step into the future, Here the horizon is at 50. So this is the error, the mean squared error of the predictions after 50 actions have been taken. And you can see that the multi-step forward model makes a bigger difference when you're at horizon of 50 than when you're at a horizon of 1. So that confirms our hypothesis that using a multi-step loss function does improve performance over a long horizon for learning a model. Now we're going to move on to context training and discussing the different architectures that we've come up with and some of the general conclusions of which methods are better. And how they can be applied. So in this environment, we're going to be looking at just a two-link pendulum for now. When we look at the variables, we start off with the state in the Cartesian space. We encode it down into 4 dimensions. Here I put Q0, Q1, Q0 dot, Q1 dot. In reality, the latent space may not actually end up being maybe some nonlinear combination of these variables, but we know that the dimension is 4, so we can approximate it with these. And the model we're learning is going to be in this lower dimensional space. And then we can evaluate how well the forward model does by decoding the latent space and seeing if it actually predicts how well it predicts the final Cartesian state at the next time step. There we go. All right, so our overall goal for learning these encoders and these decoders to learn this lower dimensional space is that we want to be able to have a forward model that can predict within the latent space and be accurate once the predicted latent spaces are decoded. So this is the final thing that we're going to be comparing performance on. But in order to learn the encoder and the decoder, we're going to compare the traditional autoencoder, which we described at the beginning, with our methods of context training. So the simplest version that we discuss, which is how I've been describing it so far, is that you take your state, you encode it, you pass that state with the action through the forward model, you predict the next latent space, then you decode it to get your predicted next full state, and then you optimize everything, which they're all neural networks, so you update all of the weights by trying to minimize the error between the true next state and the predicted next state. We also test other architectures because in some early experiments, we realized that the decoder network and the forward model network often end up, they're stacked right on top of each other. And so what the decoder learns is sometimes not separable from what a forward model learns. So we add this decoupling decoder so that the loss function contains 2 values in order to separate what the decoder learns from what the forward model learns. We also, since in our last experiment, we showed that learning models using a multi-step loss helps the final model. We figured, well, why not also test context training using a multi-step loss? So we test that here, and then we also test the decoupling decoder in the multi-step format as well. So we compare our results. We learn an encoder and a decoder using all 4 of these methods, as well as the traditional autoencoder. And then we use those encoder and decoder in order to, we extract the encoder and decoder and use them to learn a latent space forward model, which is this F here. And we compare that performance. So this is the median and mean squared error of when we use these models to predict what will happen when we take 50 consecutive actions. Here, the results are a lot less clear than with the single step and multi-step, and this is kind of this is where we highlight the importance of diving deeper into evaluating our models. So if we were to, the mean and median, you can see the median is actually generally 2 orders of magnitude better than the mean, which means there's a huge amount of outliers in all of these models. So we want to figure out really what models perform better when we ignore the outliers. And we should start first by looking at what do each of these numbers mean. So a loss of, or
Emily,
yeah,
Emily, I have a question. You said we can interrupt you. So
yes,
I'm curious, do you have with the results that you'll have now showing us, will you have an interpretation of why, for example, the MSFM is switching from being the lowest performant to the highest performant? And what's that inflection point that we have there? What is special about your application when you have a horizon of whatever it is, 12 or 11? Is that you'll have something on that also? I'm curious.
yeah. So that's I think the main conclusion that we draw from this is that, so here's the kind of the full distribution. What we found was that the multi-step forward model has, when it when it starts accumulating errors, it does so in a more extreme way. So its errors, when it goes, once it predicts something wrong, it's going to slowly predict wronger and wronger. That's not really a word, but more wrong and more wrong. Uh, it has huge sections of really bad outliers, especially as the horizon increases. And that just, but we can also see that the majority of the time it's performing, it has the best possible predictions on one subset of the data set as well. So actually in our next application, we're going to try and explain how, or we want to try and figure out, you're right, if we were to actually use this model, are we limited now to only using it up to a horizon of 10 because we don't
After
want
that.
it to be, if it predicts very extreme values that could result in damage to a robot or damage to the environment, we want to find a way to, can we figure out when the model is performing well so that way we can trust the median value instead of worrying that we're going to hit one of those outliers. So that will be in a few slides. Um, and then I guess the last thing to show is that these are kind of arbitrary values. Right now, 10 to the negative 3. Let's look at what this actually shows in the real world. So if an error, we have an error of 10 to the negative 2, that would be here. This is what predictions look like when the loss at horizon 50 is equal to 10 to the negative 2. So we say that losses of 10 to the negative 1 are generally okay. Anything above that is basically a garbage prediction. So another key takeaway is that if we look at the median, or if we could only use our model when it's, in the error of the accuracy shown in the median, we know that our model is pretty good and is going to be predicting 10 to the negative 3 is a great prediction. But however, 10 to the negative 1 is a prediction that is not useful. So you probably wouldn't want to use that, past a few steps. So how can we take these results? How can we create any kind of certainty on, or guarantee that we are only using the model when when it is confident about what it's predicting? So we do this by training an ensemble of models. So let's take the best result here, the multi-step forward model, and let's train encoders and decoders using different random seeds. And then we're going to use those models to take the same input state and same action and predict the next step. And our hypothesis is that if the model is wrong, it's going to be wrong in a random way. So, but if a model is right, they should all be right. If three different random seeds are all predicting the same output, then we assume that the model is correct. And then if they're predicting very different outputs, the standard deviation between those values will be high. And we want to know is if our seeds are uncertain, if they have a huge standard deviation, like here between the different models in an ensemble, does that mean that our prediction error is going to be higher? Like, does that tell us that we are hitting one of these outliers? So we collected a bunch of data to test as the standard deviation between predictions increases, is there a curve? Can we find a pattern between the agreement between the models versus how accurate the models are? And we do, especially at along longer horizons. For single predictions, when all of the predictions are pretty low, it's not as obvious, but when you're predicting over a long horizon, there's a general trend between the standard deviation and the actual loss that we're seeing. So if we were to plot this, these plots are a little bit tricky to understand, but let me go through it piece by piece. The X shows the standard deviation between all of the predictions. So if a model predicts is wrong, it's wrong in a random way. And so when the standard deviation between the predictions is higher, you can see that generally the actual model error is higher. We want to find a way to quantify this. So how much of the data is usable? If we have a test data set and we use an ensemble of models, let's say we cut off, we don't want to, the model is not useful if the error is greater than 10 to the negative 2. So we want to find a way to keep all of the data that generally is going to have a loss or an error of 10 to the minus 2 or less. And we can do that by creating a standard deviation threshold. So if we limit our standard deviation between our models to be less than 0.1, we can see that about of all the data that is below the standard deviation of 0.1, about almost 100% of the data has a model error of less than 10 to the negative 2. So if we throw out any test data that has a standard deviation higher than that, maybe we end up throwing out a lot of our data, but we can be assured, not in rigorous theoretical, in a proof sort of way, but in a soft guarantee that anything below a standard deviation of 0.1 will have a very accurate prediction. If we're okay with having a few more outliers, we can increase the standard deviation and then also keep a higher percentage of our total data. So this is a very interesting observation that we made, which was only possible due to a lot of the in-depth analysis that we were doing on our forward models. If we had stopped and just looked at the mean and median and just said, okay, well, this is good enough, or the mean is too high, so let's just throw it out, we would not have been able to come to this conclusion. The next step in this research would be to begin applying it in a controller and only using our model when the standard deviation is below a certain threshold and seeing if that improves how controllers work, if it can be guaranteed to have a higher accuracy. Here's just another plot using a slightly lower model error threshold. So that kind of concludes a lot of the research around improving long-term accuracy, context training, um, and then model evaluation and model agreement. I think I've run out of time and I want to leave some time for questions. Uh,
You,
I'll
you can
do,
you can take a little bit more time.
okay.
Yeah.
I'll just kind of skim over some of the applications. So we wanted to try applying some of the things we learned into robot motor control applications. So we started by using proximal policy optimization, which is a model-free RL algorithm. We wanted to see if the latent spaces we learned using using our different context-trained encoders, if we encode our state using those encoders before it gets input into the policy, would that improve the policy that we end up learning? And this result was uh, we used it on a two-link pendulum. One of the difficult parts of the model-free algorithm we used actually struggled a lot to learn a policy that could even, we wanted it to have the end effector of the pendulum reach a goal. So find a goal position. We had to severely limit the angles that the pendulum could go to, and then limit the, here in the orange is where the goal is allowed to be randomly placed when you're generating policies. Um, Even with that, we found it difficult to learn a policy using the original state space to find, to like very consistently be able to reach the goal. So even with this small problem, that was difficult. And there was a wide variation in how well the policy learned from given different random seeds. So when we tested it, the encoders we learned via context training, the difference in the methods of the single step versus the multi-step for the decoupling decoder, there didn't seem to make enough of a difference. The true model, the difference between the methods was actually bigger than, let me explain that better. We tested a bunch of different seeds too for each method. The variation between the different seeds was higher than the variation between methods. So from that, we can't really conclude. The conclusion is that it did not help with um, this model-free reinforcement learning when we were using it to create the observation for the policy. There could be a few different reasons. Maybe the policy, the algorithm that we were using, the proximal policy optimization, maybe it just didn't help for that one. It's also possible that the differences in the latent spaces weren't big enough for it to matter for model-free reinforcement learning, because model-free reinforcement learning can be more robust to errors. And so maybe having a better latent space didn't actually change how well it performed. And then leaving on a higher note, that was not successful, but we do talk about now applying it to, or if we do have a very high accuracy model, how powerful is model-based control, specifically model predictive control? When using a model, what can we do with it to achieve robot motor control? So this is the same. We use the model in our imagination to test different actions and choose the best one. We take an action and then observe the changes and do this all over again. In this research, we used a simulated snake and we tested how well model predictive control worked when our model simulated different environments for a snake. So we simulated a snake on the ground using dry friction. We simulated a snake, or more like a tadpole, like viscous friction, which really only applies to very small fish or tadpoles. And then we also tested changing our model to include fluid dynamics and added mass, which would be more like an eel. Our results were that given the no matter how much our model changed to adapt to the environment, to show different environments, model predictive control was able to generate gates that represented that seemed to match what you would expect in the real world for dry friction, viscous friction, and fluid dynamics. So this shows that if we can learn models that are accurate, or even models that can change for changing environments, that we do not that model predictive control is very powerful. The alternative method to using model predictive control would be to use a PID controller using an analytical snake gate generator. And when we tested that, we found that every time we changed the model, we had to change a lot of parameters in order to optimize and get a gate that worked again. Using model predictive control, as long as the model was there and made physical sense, the controller was able to adapt the motion in order to achieve forward locomotion in that environment. So once we start learning models, we can start placing them in a model predictive control setting and see how they perform. The other benefit is that as long as models are fairly accurate, they do not have to be perfect. Model predictive control is able to adapt and still generate locomotion with model errors. So so some of the models we learned earlier that were in the latent space, as long as if there's a few outliers, I think model predictive control will be okay, as long as we can generally keep our models into a fairly accurate range. Error over even up to 25% on some of the coefficients of friction, the controller is able to handle it. So these are very visually pleasing results, and it shows the power of models in general. And kind of this was the first work we did at the beginning of my research, and after doing this, we realized how important models were, and that's kind of where the rest of the work was derived from. And so future work would be taking a lot of the models that we learned, or learning a model for the snake and not just the pendulum, and testing them in environments like this. So in conclusion, the two main contributions of this work are that we were able to improve the long-term accuracy of learned forward models by simply increasing the number of adding temporal data, or increasing the number of time steps that we put into the loss function. This seems like this is a pretty simple result, but it's also very powerful because this is something that we weren't using like an LSTM. This is just using a single model and predicting multiple steps and using that as our loss function. It's something that any learned model can encode. You can easily implement this, so it's a like a very simple way to improve any model. So we hope it can be applied to any kind of robotic system. The second is that our method of learning a lower dimensional latent space using context training, we were able to improve the long-term accuracy of our learned forward models that operate in the latent space, by using context training to learn the encoder and the decoder. The general result is that let's start with the single step architecture. The results I showed were for the 2-link. In general, the simple autoencoder and the single step forward model context do not, depending on which system we tested it with, we tested it on a 1-link, 2-link, and 3-link pendulum. It kind of alternated back and forth, but in general, I would not be confident saying single step forward model actually improves over the autoencoder. I think sometimes it got lucky, but the single step forward model with the decoupling encoder always improved performance, um, and significantly improved the long-term predictions of the latent space forward model. Then when we moved on to the multi-step forward model, we found that multi-step, the multi-step architecture for the context training was almost always better than the single step plus the decoupling decoder. And they were always both better than the simple autoencoder. We found that actually adding the decoupling decoder to the multi-step tended to just make things less stable. Using a multi-step loss seems to act as a decoupler on its own, so it's not necessary for the multi-step architecture. And throughout all of these experiments, we found that doing in-depth model evaluation is very important. Being able to compare not just the mean and median, but the overall distribution and looking at the outliers is very important for being able to determine which model performs better. And then in terms of actually using the models that we learn, we found that by using an ensemble of models, if we train a bunch of models using one method, as long as they agree on the prediction they make, we can be pretty confident that the loss is going to be small enough to be useful. So it's going to be under the threshold. So if we set the standard deviation between predictions to be 0.1, we know that when we're using our model, that we can generally guarantee that it's going to be fairly accurate. And so then if we can if we can say that, okay, our models are generally only going to be used when they fall below the median loss, then the ranking of our models is much easier to determine. And that's where like we would definitely want to be using the multi-step forward model, or the single step with the decoupling decoder. But being able to analyze that and then use that in order to keep the benefits of certain methods and then throw out the disadvantages is very important. Finally, the applications that we tested, the context training, although it improved accuracy for latent space forward models, it did not improve performance when it was used to encode the observation for a model-free RL. This definitely needs more research looked into it, because this was just one example, but right now it wasn't it didn't make much of a difference there. But we do know that when we have accurate models, that is very important for using model-based control. And so applying a lot of these methods is going to be very exciting. Hopefully the student who takes over after me will be able to really see some of the benefits of the methods that we've used in generating gates or performing dexterous manipulation for some of the tactile equipped hands in our lab. Yeah, thank you for taking the time to listen today. And yeah, let me know if you have any questions. And
Thank
I'm
you, Emily.
definitely open to comments and feedback for my thesis next week as well.
Thank you, Emily. That was a great talk. I have a few questions.
Yes.
In the interest of time, I'm jumping in here.
Yeah.
So I don't know if you're familiar with the work from Chelsea Finn from Google Brain on hierarchical foresight. So I think a lot of what you're talking about reminded me of some of the work we've read from Chelsea Finn. If you're not familiar, might be a good read for you.
Yeah. Okay.
I think they in their context they use something called sub goals, but it's really to predict these long horizon tasks in
I see.
URLs. So it might be a good reference if you're not familiar with that work.
Thank
The
you. Yeah,
question, I have for your work is how much performance improvement did you get with using this, AE models, or you have used different variations with the context, but what is the performance improvement you received? I know there was one slide which you went
Yes.
through, so over the
So
horizon, yeah.
over a horizon of 50 steps, we get
Mm-hmm.
about an order of magnitude between a regular autoencoder and like the best, which would be the multi-step or the single step with the decoupling decoder, which is the difference between fairly, I guess both can perform. This is only looking at X1. When you look at a lot of, sometimes the like the velocities of X and Y, that tends to be where this is the sum of X, Y, the positions and velocities. Velocities tend to be the bigger components in the error. So this loss decrease is generally more accuracy in the velocity predictions. So it's not in terms of the median,
Mm-hmm.
where's the uh yeah, so this actually is a big difference even at the very beginning, but towards the end, uh not only is the median a lot lower, the absolute best predictions, so the autoencoder never is able to predict better, to have a loss of less than 10 to the negative 4. But the multi-step forward model also has a good portion of predictions that are way more spot on, which I think is one of the more important takeaways too, is that as we can actually, if we want to use the ensemble method and cut out, really choose lower and lower losses, um, we can only use, we can't use the autoencoder results for that because it has a limit to how accurate it can go. But the multi-step has a much higher maximum accuracy.
Okay. I have a few more questions, but I'll hold
Yeah.
off. I think Tej has a question here.
Mhm.
Tej?
Hello, hi. Uh, I really liked your talk. I don't know if you can see me, but yeah. So, I did have one quick question. It's
Mhm.
regarding the ensemble approach that you were talking about. So,
Yes.
in classification methods, when we use ensembling, there is always like one target class, which is the ground truth. And obviously, you can compare different ensembles and then see which the majority of ensembles agree on. But in
Yes.
robotic or kinematic control, there might be multiple solution spaces which might be correct. So you might get two ensembles which disagree, but both of them might have a solution to the space which are both correct. How would you work with this?
Um, so this is not that's more like actual kinematic control where you're trying to find the set of actions that get you to a goal. This is only looking at accuracy of a model. So given a current, the dynamics should be given your current state and an action, the model should always predict the future state should be deterministic, right? Um, or maybe there's some noise, but like you're not, there's only one right answer for the next state given the current state and an action.
Oh,
So
so we're comparing the predictions over here.
predictions, yes.
Oh, I see.
So if the
Okay.
models are all if they all agree on what the next state is, we found that if they all agree, then they're probably right. The error is pretty small. If they're all confused, they're going to be confused in different ways, and so the error is going to be a lot higher.
I see. All right, thank you.
Yeah.
I think you might have covered this, Emily. I don't see any other questions. Maybe Gabriella has question.
I'm good.
Or
I'll
I'm
let you.
jumping in. Um, so maybe you covered this, Emily, at the end, but how much loss from the autoencoder itself? You have different variations of it, right? I mean, how much reconstruction loss from the model itself that you're tolerating? And did you do some ablation studies on that?
Let's see. So, that's a good point. So that's one thing that I think, let me see if I'm answering the right question. Let me go to my extra slides. So are you asking like what we're like if we were to take the encoder and the decoder out of the scenario and use it just to encode and decode, what would the reconstruction loss be?
Right. I mean, different variants of it, right?
Yeah. I mean, right now, the way we evaluate the problem of comparing the different methods for their reconstruction loss is that some methods, their reconstruction is a single value. Oops. And then sometimes it's the two values. So the actual value that the mean squared error, like the value that comes out of these, when you're training it, the loss value isn't equivalent because sometimes it has multiple values, sometimes it has two, sometimes it has one. What we would need to do would be to take the encoder and the decoder out of that scenario, and instead of using it to train a forward model, we could also just do like here take them out and then test them alone. We did this for a very simple system where for like a linear point mass toy problem, and that one did show that like this method was not consistent. You couldn't even use them to really decode properly. We were able to bring it down into like matrices and do the math and find out it wasn't they weren't independent of the forward model. But doing it this way did allow us to do that. So that's one ablation where we showed on a very small scale that this
Right.
decoder was important. Is that kind of what you were asking, or?
Yeah. Maybe also I think I mean, because you're preparing this for next week, another
Yeah.
recommendation would be also kind of have a backup slide on what the choice of those decoder and the model architectures, what they are and why you kind of narrowed down on those architectures.
Good point. Yeah.
I know it's probably just a method in the bigger context for you, but maybe folks who are in the ML space might be more interested in why those architectures are chosen for what advantage in terms of whether it's the reduced reconstruction loss or the compression it gives at a much faster rate. Whatever the reasons are, I think it will be good to, yeah. Jorge has a question, I think.
Yes, hello. Thank you for your presentation. I just had a quick question regarding your forward model. Did you find during your research, did you find like an optimum number of forward models? I think in the test you're talking about, you only use four forward models. I was just wondering if the more the better, or is there like an optimum, or does that depend on the state?
You mean for like the multi-step?
Yeah.
We tested I think we tested 1, 5, 10, and 15, and we noticed there just wasn't much of an improvement after 5, so we just kind of stuck with it. Interestingly, there was some work that was done concurrently where they were using someone else tested this idea in a slightly different context, but they tested like every number from, 1 to 30. And I think they found that 5 was one of the better numbers, so we just happened across it. We didn't test at that scale, but 5 seemed to be all we needed for this. But that may change depending on the time scale. So between each time step is 0.2 seconds. So if that changed, I would imagine that would change how many steps you need to improve your accuracy.
Emily, is it possible that it's also dependent on the problem itself, the number of steps?
For improving?
The
Yeah, I
application.
guess it depends
Yeah.
on. We looked at, so when I chose, like we would, train it with 5 and then we'd look at the final result over a horizon of 35 or 50. But maybe if you wanted to predict only 10 steps in the future, maybe the number of steps is different. If you wanted to predict like 500 steps into the future, maybe your overall accuracy would be lower, but maybe be better to have your final, like if maybe you might need 20 or 30 lost steps if you were trying to predict way farther into the future.
Mm-hmm.
And yeah, you're right. It depends on how quickly, like how quickly states oscillate too. Because if you average out too many changes, you're going to, depends on how much detail you want to capture in your predictions.
There was a comment by one more student. Multi-step model looks like filter. Praveen Kumar, do you want to add anything more to that, or is that a question or an observation maybe?
Yeah, so like what I see over here, like increasing the number of like your the input to the model, like how you are inputting the model, and if you're increasing the number of state steps, like the previous state step that you are inputting into the model. So this is like kind of a thing that we use in robotics. So it's like filtering our states.
That's true, because you're averaging over. You've got a window where you're looking at.
So
Yeah.
so in order to answer like how many steps you need, you can go through like how you design a filter. You can use the same logic in selecting those steps. So that could be a
That's
way.
a good point. That's a good observation. Thank you.
Yeah, thank you, Praveen. Any other questions? I think Gabriella, did you have?
I'm good. I asked my question.
Okay. Thank you so much, Emily, for sharing your research with us. Wish you all the best in your defense next week.
Thank you very much, and I appreciate all the feedback and questions. Yeah, thank you very much for letting me come and give my talk.
Thank you, Emily. Have fun next week.
Thank you. Awesome.
Bye.
Bye.
Bye.